We will now continue to solve problems using method of sections into our current topic, that is analysis of statically determinate plane truss. The requirement of this truss is to solve for member force Fj, Jk, Gc, Bc, and Fg. We have some simple steps to follow in order to solve for the problem. The first step is to check the determinacy of the truss. Second step is to solve for the support reactions. The third step is to pass cutting plane that will cut the portion of needed truss member force. And the fourth step is to replace the severed members by a force. And for the fifth step, we will apply equations of static equilibrium to solve for the member forces. We will now start in step number 1. We check the determinacy of the truss. We will count the number of members, joints, and support reactions components. Total member of this truss is equal to 19. Number of joint is equal to 11. Support reactions are equal to 3. 2 for hinge support and 1 for a roller support. If we substitute the value into m plus r, that is equal to 22, and to twice j, that is also equal to 22. If m plus r is equal to twice j, that is statically determinate. We can recall that if the truss is unstable, there's no need to continue the calculation. If the truss is statically determinate, then we can apply equations of static equilibrium to solve the member forces together with the support reactions of the truss. If the truss is statically determinate, equations of static equilibrium were not enough to solve for the problem. For statically determinate trusses, we can proceed to the calculation after studying about truss deflections. We will now continue. Step number 2. We solve the support reactions. AX is assumed to be acting to the left. AY and EY are upward. If after we perform the operation and the result is negative, assume direction was incorrect. We will now apply summation forces along X. Rightward forces are positive. So 10 kN at J and 10 kN at joint F are acting to the right, so those are positive forces. And for AX, that is negative, since AX is assumed to be act leftward or to the left. From that equation, we can be able to solve for AX, and that is equal to 20 kN. Since this is positive, our assumption for direction of AX was correct. That is a leftward support reaction at point A. We will now apply summation moment at point A in order to solve for EY. We assume that clockwise moment are positive. We can observe that the 10 kN applied at point J with a moment arm of 8 meters will rotate clockwise moment with respect to point A. And for the 10 kN applied at joint F, the moment arm is 4 meters, that is also clockwise with respect to point A. For the 30 kN at point C, that is also clockwise with respect to point A, the moment arm is 3 plus 3. 20 kN at point D, the moment arm is 3 plus 3 plus 3, that is 9 meters, clockwise with respect to point A. As we can observe, 10 times 4 is positive, clockwise. 10 times 8 is also positive, clockwise. 30 times 6 is also clockwise. 20 times 9 is also clockwise. But EY will rotate in a counterclockwise moment with respect to point A. And the moment arm is equal to 12 meters. The reason why we can observe that that is negative in the equation. So from this equation, we can be able to solve for EY, and that is equal to 40 kN. Since EY is positive, assume direction was correct. We will apply summation moment at E is equal to 0, assuming that clockwise moment again are positive. With respect to joint E, we have 10 kN at F. The moment arm is 4 meters, that is a clockwise moment. 10 kN at joint J, moment arm is also equal to 8 meters, that is also clockwise moment with respect to joint E. The 30 kN at joint C will rotate in a counterclockwise direction with respect to E. Moment arm is 3 plus 3, that is 6 meters. And for the 20 kN at joint G, the moment arm is equal to 3 meters, that is also a clockwise moment. So for 30 and 20 kN of applied at point C and D, those are counterclockwise moment, and 10 kilonewton applied at F and J are clockwise moment. So 10 kilonewton is positive, another 10 kilonewton is positive, the 30 kilonewton at joint C is negative, and the 20 kilonewton at joint D is negative, since those are counterclockwise moment. We can also observe that AY is clockwise with respect to point E. The moment arm is 12 meters, so that is positive moment. From this equation, we can be able to solve for AY, and that is equal to 10 kilonewton. Since 10 kilonewton came out to be positive, assumed direction was correct, AY is an upward support reaction at point A. We can apply summation forces vertical to verify if our answer was correct. Forces applied downward should be equal to the forces applied upward. So AY plus EY should be equal to 30 plus 20. So if we replace the value of AY and EY to this equation, apply summation forces vertical, we can observe that 10 minus 30 minus 10 plus 40 is equal to 0. 0 is equal to 0. That is satisfying summation forces along vertical is equal to 0. We will now proceed to the third step. We will pass cutting plane at the location of the desired truss member force. Frequently, more than one member is being cut. Dividing the whole truss into two parts, we draw the free body diagram, considering the portion of truss acted upon by least number of forces. So this is very important. It will simplify the calculation if we can follow this important hint on solving the problem. There were cases where we cannot directly obtain member forces by passing a single cutting plane, like member force FG of this truss. If we pass this cutting plane, we have left with 4 unknowns, 1, 2, 3, 4 unknowns. We cannot directly obtain for those member forces since we have only 3 equations available. If we have 4 unknowns, we cannot solve for the problem. The technique is to find a way where we can reduce the number of unknowns. In our case, we can pass this cutting plane to solve first for member force BC. After solving for member force BC, we can pass this cutting plane. We have left with 3 unknowns, 1, 2, and 3. We have 3 equations of static equilibrium. Thereby, we can now solve for those member forces after solving for BC, because BC will be obtained by using this cutting plane and the left part as free body diagram. So I select the left part as free body diagram to solve for member force JK, GC, and member force BC. So originally, we have 3 unknowns if we pass this cutting plane and draw this free body diagram, that is CG, JK, and BC. But since CG is an inclined member force, we have to solve for its vertical and horizontal component. We will apply the equations of static equilibrium to this free body diagram in order to solve for the 3 member forces CG, JK, and BC. So we have 3 unknowns, we have 3 equations of static equilibrium. We can solve for the unknown member forces. The technique here is to find a joint wherein 2 member forces will intersect. In our case, we have 2 joints where 2 members will intersect, that is at joint C and at joint J of this truss. If we apply summation moment at point C, we can eliminate CG and BC since those member forces will pass through the moment center at joint C. We have left with only one unknown, that is JK. If we apply summation moment at joint J, JK and CG will pass through the moment center, that is at joint J. Thereby, we can only have one unknown, that is member force BC. Okay, so we will now proceed. We will apply summation moment at point C is equal to 0. Applying summation moment at point C, we have 1, 2, 3, and 4 member forces that will create moment with respect to point C. So we have 4 terms on the equation. For the 10 kilonewton reaction at point A, moment arm is 3 plus 3. That is a clockwise moment with respect to point C. And the 10 kilonewton at joint F, moment arm is 4 meters. That is also a clockwise moment with respect to joint C. 10 kilonewton at J, moment arm is 8 meters. That is also a clockwise moment with respect to point C. And the last term of the equation, that is member force JK, moment arm is 8 meters, that is a counterclockwise moment with respect to joint C. We can observe that 10 is positive, that is clockwise. Another 10 kilonewton is positive, that is also clockwise, that is the load applied at joint J. And 10 multiplied by 6, that is the support reaction at point A, vertical. Moment arm is 3 plus 3, that is 6 meters. And JK multiplied by 8 meters, that is a counterclockwise moment, therefore that is negative. From this equation, we can be able to solve for JK, and that is equal to 22.5 kilonewton. Since 22.5 came out to be positive, our assumption that JK, which is acting toward the free body diagram, was correct. That is a compressing force. So I write here that is compression. We will now apply summation moment at point J to solve for member force BC. We know that CG and JK will intersect at joint J. Thus, those member forces will not create moment with respect to joint J because they will pass through the moment center. Here is now our equation. Assuming that clockwise moment are positive, we have AX 20 kilonewton at point A. Then we have AY 10 kilonewton at point A. Then we have BC, the member force acting on this member. Then the force acting at joint F. Here is the force, that is 10 kilonewton in this equation. So if we replace the value of AX, that is 20 multiplied by 8, clockwise moment with respect to joint J, then we have 10 kilonewton, that is the vertical reaction at point A. The moment arm is equal to 3 meters. So here is the moment arm of the force with respect to joint J, that is a clockwise moment. So we can observe that 10 multiplied by 3 is positive. 20 multiplied by 8, that is the horizontal reaction at point A, that is also positive, that is clockwise. Then for BC, that is negative. Since BC moment arm is 8 meters, will create a counterclockwise moment with respect to joint J. And for the 10 kilonewton applied at F, that is also a counterclockwise moment with respect to point J. Moment arm is equal to 4 meters. So from this equation, we can be able to solve for BC, and that is equal to 18.75 kilonewton. Our assumption that BC is under tension was correct because 18.75 kilonewton came out to be positive. To solve for member force CG, we can apply either summation forces along vertical and summation forces along horizontal. If we apply summation forces along horizontal, the horizontal component of CG will be involved in the equation, and if we apply summation forces vertical, the vertical component of CG will be involved in the equation. But before we can apply summation forces vertical and horizontal, we have to resolve first the vertical and horizontal component of member CG. Here is now our reference triangle to solve for the vertical and horizontal component of CG. For the vertical component, that is equal to the vertical dimension divided by the hypotenuse of the triangle, that is square root of 4 square plus 1.5 square, or square root of 18.25. So if we perform the operation here, the result is 0.936 of CG. For the horizontal component of CG, that is just equal to the horizontal dimension divided by the hypotenuse of the triangle, that is 1.5 divided by square root of 18.25. If we perform the operation, that is equal to 0.351 of CG. This reference triangle was taken from the given truss. We can observe that this is equal to 4 meters, and this distance is equal to 3 divided by 2, that is 1.5 meters. So we have 1.5 and 4 meters to solve for the vertical and horizontal component of CG. We can apply summation forces vertical or horizontal to solve for member force CG. But we can observe from this free body diagram that we have 1, 2, 3, 4 and 5 for the horizontal forces compared to the vertical forces that is 1 and 2 forces only. So if we apply summation forces along vertical, we have only 2 terms of the equation compared to 5 forces if we apply summation forces along horizontal. It is more easier to solve CG using summation forces along vertical. So here's now our equation. AY is upward, that is 10 kN, and the vertical component of CG, that is 0.936 of CG, is downward, so that is negative. From this equation, we can be able to solve for the value of CG if we replace AY into its equivalent, that is equal to 10 kN, and CG will be equal now to 10.68 kN, that is positive. So member force is under tension because it is acting away the free body diagram. Here is now the proof that if we apply summation forces along horizontal, we can be able to solve for the value of CG, and that is also equal to 10.68 kN. So we know that we have a value of BC, we have value of the horizontal component of CG, then 10 kN applied at joint J, 10 kN applied at joint F, the horizontal reaction at point A, and the member force on member JK. We equate that to 0, that is, applying summation forces along horizontal is equal to 0. Here is our free body diagram. We replace the value of BC, that is 18.75, then 0.351 CG for the horizontal component of CG, 10 kN applied at point J and at point F of the truss, then 20 kN the horizontal reaction at point A, 22.5, that is the member force acting on member JK of the truss. The only unknown from this equation is CG, and that is also equal to 10.68 kN, and it is also under tension. If we compare to this equation, we have only 2 terms of the equation, so it is more simpler to apply summation forces along vertical compared to summation forces along horizontal. I hope you learned from these 2 equations. After solving for member force BC, GC, and JK using this as a cutting plane, we can now pass another cutting plane. Here's the cutting plane to solve for member force BG, FG, and FJ. After we pass cutting plane, we can select the right part or the left part of this cutting plane as free body diagram. If we select the right part as free body diagram, we can observe that it is more complicated to solve for the unknown member forces rather than using the left part as free body diagram. So therefore, I will select this left part as my free body diagram to solve for the unknown member forces. Here is now our free body diagram as we pass this cutting plane and select the left part as FBD. We will replace the severed members with the force. So we have FJ, FG, and BG because we have already solved for member force BC, and that is equal to 18.75 kN. But since FJ is an inclined member force, we will solve the vertical and the horizontal component of this member. Here is now the vertical component of FJ, that is FJY, and for the horizontal component, that is FJX. So for the vertical component, that is equal to the vertical dimension divided by the hypotenuse of the triangle, that is 4 square plus 1.5 square, and that is equal to 4 divided by square root of 18.25. So if we perform the analysis, that is equal to 0.936 of FJ. And for the horizontal component, that is equal to 1.5 horizontal dimension divided by the hypotenuse of the triangle, that is also equal to square root of 18.25. If we perform the operation here, that is equal to 0.351 of FJ. But since we know that BG have the same inclination to FJ, that is also the vertical component and horizontal component of member force BG. This reference triangle was taken from the given dimension on the truss. we know that this vertical dimension is equal to 4 meters and the horizontal dimension is equal to 3 meters divided by 2, that is equal to 1.5. So we have 1.5 for the horizontal and 4 meters for the vertical. For member force BG, this is equal to 4 meters and this distance is also equal to 3 meters divided by 2 or 1.5 meters. So they have the same inclination to member force F. We will apply summation moment at the joint where two member forces will intersect. That is the technique that we learned. We will find a joint wherein two member unknown forces will intersect. In our case, we have joint G together with joint F. We can observe that at joint F, FG and FJ will intersect, BG and FG will intersect. So we will select joint G and joint F as our moment center to solve for member force FJ and BG respectively. We will now proceed to the calculation. We will apply summation moment at point G. Clockwise moment are positive. Since the horizontal component of FJ will pass through the moment center together with FJ and BG, they will be eliminated from the equation. So the forces that will create moment with respect to joint G will be the horizontal reaction at point A, the vertical reaction at point A, member force BC that is equal to 18.75 kN together with the vertical component of FJ. With respect to joint G of the truss, AY multiplied by its moment arm that is equal to 4.5 meters is a clockwise moment with respect to joint G, that is clockwise. Then AX, that is 20 kN, the moment arm is equal to 4 meters, that is also a clockwise moment with respect to joint G. Then for the vertical component of FJ, that is FJY multiplied by its moment arm that is equal to 3.0 meters, that is also clockwise with respect to joint G. And for member force BC, the moment arm is equal to 4 meters, that is a counterclockwise moment with respect to joint G. Here is our reference. Here is our moment center. Arm will be the center of the clock. Then this is the clockwise rotation, and the opposite of that is the counterclockwise rotation. We can now replace the value of AY, AX, FJY, and BC. And from this equation, the only unknown is FJ, and that is equal to 17.81 kN. Since the result is negative, therefore member force is under compression because we assume that FJ is under tension and it came out to be negative. Our assumed direction was incorrect. It should be under compression. We will now apply summation moment at joint F of this free body diagram. So we can observe that FJ together with the 10 kN applied at F will intersect to its moment center. So those forces will not create moment with respect to joint F of the truss. So the forces that will create moment with respect to joint F will be the vertical reaction at point A, the horizontal reaction at point A, member force BC, and the vertical component of BG. We have already obtained the vertical component of BG, and that is equal to 0.936 of BG. So with respect to joint F, we have 10 kN that is a clockwise moment with respect to joint F, 20 kN that is also a clockwise moment with respect to joint F. Then we have BG that is a counterclockwise moment with respect to joint F. Then member force BC that is also a counterclockwise moment with respect to joint F. So we can replace the value of AY, AX, the vertical component of BG together with BC to this equation. So all clockwise moment are positive and for the counterclockwise moment are negative. So from this equation, the only unknown is BG. We can obtain for member force BG, and that is equal to 7.12 kilonewton. So since 7.12 came out to be positive in the calculation, our assumed direction for BG that is acting away the free body diagram was correct, and that is under tension. We can now proceed to calculate for member force FG. We can perform the calculation by using summation forces along horizontal or vertical. I select equation of static equilibrium summation forces along horizontal to solve for member force FG. So rightward forces are positive. I have 10 kilonewton, that is the force applied at joint F. Then BGX, that is the horizontal component of VG. We have member force BC. We have already obtained the value of BC. AX, that is the horizontal reaction at point A. And member force FG, that is the unknown member force on the equation. We will now replace the value of BGX, BC, AX, FJX to solve for member force FG. So the horizontal force applied at joint F is 10 kilonewton. That is equal to 0.351 multiplied by 7.12 kilonewton, that is equal to 2.5. Then member force BC, that is equal to 18.75, 20 kilonewton, that is the horizontal reaction at point A. 6.25, that is the horizontal component of FJ, that is also equal to 0.351 multiplied by FJ, that is equal to 17.81. So the result is equal to 6.25. So from this equation, we can observe that FG is the only unknown, and that is equal to 5 kilonewton. So since 5 kilonewton came out to be positive, our assumption that FG is under compression that is acting toward the free body diagram was correct. To those who wants a copy of this file in PDF, comment down below your email ad, like and subscribe, and I will send it to you.